Continue with the discussion on dipole. I think you remember, if I consider a dipole, Q is a positive charge and minus Q is the negative charge. Two equal charges but of opposite nature, they form a dipole. And we had a convention that all the distances are to be measured from the center of the dipole. Let it be equal to A from one to the one charge, and to the other charge it is another A. Now on the axial line we select a point. Let me call that as M. Here I want to find the intensity. Whenever we want to find the intensity, we have the practice of keeping a +1 coulomb charge there, isn't it? We need to measure the intensity of that. Try to understand. Now this charge at M is interacting with two charges, one at A, other at B. Charge at A being a positive charge will repel it. I am marking the repulsion like this. This is electric intensity due to the charge at A. You are understanding, I think? Charge at A is Q. Q is now repelling +1 coulomb charge. As a result, I am directing the intensity this way. Now if you consider the negative charge will attract it. Longer vector, I call this as EB. It is very clear that EB is greater than EA. I think you have followed all these things. And finally, resultant electric intensity, which is EB minus EA, was found to be 1 by 4 pi epsilon naught. Try to understand, we have done this derivation. 1 by 4 pi epsilon naught, 2p divided by r cube we ended up with. 2p by r cube. E on the axial line. Okay. Actually it was the other way. 2pr divided by r square minus a square whole to the power of 3 by 2 we got for any closer point, where r is this distance from the center to the point where you are considering the intensity, which should be marked, we should mark the distance as r. In that case, it is 2pr divided by r square minus a square to the power of 3 by 2. Or I can write this with an approximation. What was the approximation made? We said that r is much greater than a. What does it mean? We are now considering a point M far from the dipole. When you consider it very far from the dipole, r will be a very large distance compared to a. When r is very large compared to a, E axial reduces to, E axial is equal to 1 by 4 pi epsilon naught 2p by r cube. I think you can follow the simplification. What did I do here? Since r is much greater than a, I have dropped a. A is a small number. A square is much more smaller. I have just dropped it, and you are left with only r square to the power of 3 by 2. R square to the power of 3 by 2. Isn't it? Adana reduce madidre, it is 2p by r cube. Okay. So finally we ended up with this result. Therefore here afterwards, just a minute, P is greater than EA. Therefore resultant intensity is EB minus EA. Or E axial finally was equal to 1 by 4 pi epsilon naught 2pr by r square minus a square whole square. Since r is much greater than a, you have considered now a point M very far from the dipole. In that case, r is much greater than a. When r is much greater than a, E axial reduces to 1 by 4 pi epsilon naught 2pr ಇದೆ. R square, A is negligible, R power 4, 1 R goes to the other, you end up with this result. Okay, 2p by r cube. This is for a point on the axial line. Keep this on one side. We mark this as some M where we keep a plus 1 coulomb charge. Positive charge repels it this way. I call this as intensity due to A. And negative charge will attract it. This is intensity due to B. Now these two intensities produce a resultant along this direction, and that intensity has been found to be E on the equatorial line was found to be 1 by 4 pi epsilon naught 1 by 4 pi epsilon naught P by R cube. We ended up with P by R cube. If we simplify in the same sense, you get this result. Already we have done this derivation. I need not repeat. Okay. Now if you compare these two equations, equation 1 and equation 2. In both the cases, the distance of the point under observation from the center of the dipole is R. Here also this distance has been marked as R. So for the points at the same distance from the dipole, if you observe the intensities at axial line and at equatorial line, you can come to a conclusion. What is that? E axial, if I divide this by E equatorial, try to understand, E axial is being divided by E equatorial, 4 pi epsilon naught 1 by 4 divided by E equatorial. What is that? 1 by 4 pi epsilon naught P by R cube. 1 by 4 pi epsilon naught goes with another 1 by 4 pi epsilon naught. P by R cube, P by R cube. So finally, the result that can be concluded is, for points at the same distance, intensity on the axial line is equal to 2 times the intensity on the equatorial line. 2 times the intensity on the equatorial line. Okay. So this is an important result which you must remember. Must remember this. Very important. Okay. Content is quite clear, I feel. Now we'll move on to another idea. In the beginning of this lesson, that a single charge, monopole, always produces a non-uniform field. If you consider a single charge producing the field at no two different points in the field, if I say call this as A, B, C, D, so many such points if you select, at each and every point you will find a different intensity. Intensity at A not same as intensity at B, not same as intensity at C, not same as intensity at D. Either they will differ in terms of magnitude or in terms of direction or maybe in both. Therefore, a single charge can never produce a uniform electric field. But then how to produce the uniform electric field? What is the meaning of uniform electric field? Let's follow that. Very simple. I am considering now a charge Q. This is separated by a distance, say a certain distance D from another negative charge. I am considering a dipole arrangement where a positive and negative charges of the same magnitude have been separated by some finite distance. Now try to understand this idea. At some point here, I keep a plus 1 coulomb charge. At some point here, I am keeping a plus 1 coulomb charge. See what happens. Positive charge will repel it. Negative charge will attract it. See, repulsion, I am writing a longer vector. For attraction, I am writing a shorter vector. So repulsion is more at that point than the attraction. Why? Because repulsive agency is closer, whereas attracting agency is bit far. Therefore, attraction magnitude is smaller than the repulsion magnitude. For example's sake, let me assume that here I have, at this point, I have 1 Newton of attraction and 9 Newton of repulsion. 1 Newton of attraction and 9 Newton of repulsion. Attraction 1 Newton, repulsion 9 Newton. But both the forces, repulsion and attraction from that side, they are in the same direction. Therefore, the total force, if you want to find the resultant of two vectors in the same direction, what do? You simply add the two. It becomes 10 newtons, isn't it? 10 newtons as the force existing at that point, or intensity, because force on 1 coulomb charge is itself intensity. Since I have considered 1 coulomb here, it is intensity equal to 10 newton on 1 coulomb. It was 1 newton on 1 coulomb, 9 newton on 1 coulomb. Okay. Now if I move further, if I come to this point, see what happens. Positive now finds a reduction in the magnitude of its repulsion, isn't it? Because now the distance has increased. ಸ್ವಲ್ಪ distance ಜಾಸ್ತಿ ಆಗುತ್ತೆ ನೋಡು, force ಕಮ್ಮಿ ಆಗುತ್ತೆ. Repulsion reduces a bit, but it is moving closer to the negative charge. Attraction improves. Attraction improves. Maybe the situation is somewhat like this. Attraction has increased to 2 Newton, repulsion has come down to 8 Newton. But remember one thing, in spite of the changes in attraction and repulsion, the resultant magnitude is still remaining the same. It is 10 Newton on 1 coulomb. That didn't change. Now we come to the midpoint of the line joining two charges. At that point we may have a situation something like 5 Newton per coulomb of attraction and 5 Newton per coulomb of repulsion, because now this point is equidistant from both positive and negative charges. As a result, the total intensity will be once again 10 Newton on 1 coulomb. 10 Newton on 1 coulomb. You are understanding? Therefore, at every point along the line joining the two charges, intensity is of the same magnitude and always it is directed in this direction. Therefore, in between these two charges, at every point, the electric intensity is remaining same in terms of both magnitude and direction, and such a field can be considered as a uniform electric field. Just understand, whenever the field remains same in terms of both magnitude and direction, must understand, since it is a vector, magnitude as well as direction, both of them, they need to be the same. Only when magnitude and direction both are identical, you can say that the field is uniform, whereas it was not the case here. Therefore, to produce a uniform electric field, we need dipole arrangement. Okay, I think you have understood. To produce a uniform field, we need a dipole arrangement. Let me rub this. A uniform electric field of quite a large area. How do I do that? I take a metal plate. See, this is a metal plate. This is another metal plate placed parallel to the first. These two are the two metal plates which have been placed parallel to each other. Say they are of same area also. Now, I create one positive charge on this and same amount of negative charge I place it here. Similarly, I consider one more pair. Like this, say we have pairs of positive and negative charges in very large numbers. Each pair of positive and negative charge will form an electric dipole. It will form what? An electric dipole. In the electric dipole, as you have followed, there is a uniform electric field existing between the two and directed from positive to negative charge. Remember, electric field direction. What is the direction of the electric field? Try to remember this. Direct electric field is always from positive to negative, whereas direction of the dipole moment, try to follow, direction of the dipole moment, that is always from negative to positive. You must remember. Okay. Electric field from positive to negative. Dipole moment from negative to positive. Now, there is a uniform electric field like this, directed from positive to negative. Same kind of uniform electric field you can expect between the other pair of dipoles. Likewise, there are so many such pairs which are forming dipoles, and therefore every pair produces a uniform electric field. Therefore, in the whole region between the two plates, you can expect a uniform electric field to exist. Therefore, if somebody is asking me what is the intensity here, and if I practically find that it is 10 Newton on 1 coulomb, it should be the same 10 Newton on 1 coulomb everywhere. 10 Newton on 1 coulomb. This is also 10 Newton on 1 coulomb. Here also 10 Newton on 1 coulomb. Likewise, everywhere you are finding the same 10 Newton on 1 coulomb. Means intensity is same everywhere in the region between the two planes. So if it is E here, it is E here, it is again E, it is once again E, and it is E. Likewise, everywhere you find the same electric intensity. Okay. So this is the meaning of uniform electric field. I think you have followed. To produce uniform electric field, we need a dipole. If I consider a single dipole, I will be able to produce the uniform field along a line. Now if I consider an array of so many dipoles connected or placed on some charged plates, then you can have a large area and volume producing uniform electric field. Okay. Over this area, within this volume, you are finding uniform electric field. This is how uniform electric field is established. I think you have understood this. Try to follow the behavior of a dipole in an electric field. We will follow the behavior of dipole in an electric field. Must understand it. Very easy to follow. This is a positively charged plate. This is the negatively charged plate. See, I am not writing so many negatives here, so many positives, but I have told you how it exists. Simply I am representing this as positive, this as negative. There are so many positive charges on this, many negative charges here, and they are all forming dipoles, and dipoles will produce uniform electric field in the region between the two plates. Okay. Now let me keep a dipole here. So many dipoles are producing uniform field, and in that field I am considering another single dipole. Another single dipole. You must understand. Now, ಎಷ್ಟೊಂದು ಡೈಪೋಲ್ಗಳು ಸೇರಿ ಒಂದು ಯೂನಿಫಾರ್ಮ್ ಫೀಲ್ಡ್ ಅನ್ನು ಪ್ರೊಡ್ಯೂಸ್ ಮಾಡಿದೆ. ಆ ಯೂನಿಫಾರ್ಮ್ ಫೀಲ್ಡ್ ಅಲ್ಲಿ ನಾನು ಇನ್ನೊಂದು ಸಿಂಗಲ್ ಡೈಪೋಲ್ ನ ತಗೋತಾ ಇದ್ದೀನಿ. So Q and minus Q are the two charges of the dipole. Okay, placed in that uniform electric field. Say it is pivoted something like this. ಇದನ್ನ ಹೀಗೆ ಇಟ್ಕೊಂಡಿದೆ ಅಂತ ಇಟ್ಕೊ. ಒಂದು ಡೈಪೋಲ್ ನ ಈ ರೀತಿ ಇದಕ್ಕೆ ಅಂಟಿಸ್ಬಿಟ್ಟು ಹೀಗೆ ಇಟ್ಕೊಂಡಿದೆ. Okay. So it can rotate, dipole can rotate now. It will not fall down because there is an agency which can hold it like this. Okay. Now, negative charge will repel the negative charge of the dipole. Positive charge will repel the positive charge of the dipole. Now observe carefully. These two charges are experiencing electrostatic force. What is that force given by? We know that electric intensity is given by force on unit charge, isn't it? You have written this expression E is equal to F by Q. So in that case, force, electrostatic force will be equal to EQ. Electrostatic force will be equal to EQ. Therefore, this charge is experiencing a force EQ in this direction. The other is experiencing force of the same EQ because charges are same, intensities are also same in the region between the two plates, and the field is same, charge is same, force illest illo ashte. So why don't you put this negative sign here? No, I have told you in the calculation of force and intensity, we will not consider the negative sign. What we consider as only the magnitude of the charge. Then what is this minus sign meant for? It is for indicating or judging the direction of the force. So this tells you that negative will be repelled by negative, positive attracts the negative, and therefore force is like this. This positive sign tells you that positive repels this and negative attracts this, and direction is like this. F is equal to EQ downward, F is equal to EQ upward, but both the forces are of same magnitude. You must remember. Therefore, in first year you have studied, when two equal forces act in opposite directions, they produce a couple, and couple always has the tendency to set the body into rotational motion. So couple always has the tendency to set the body into rotational motion. Therefore, it starts turning. It is experiencing now a torque. It is experiencing a torque. Now let us calculate the torque magnitude. Okay. See here. Now after experiencing that torque, it has turned through certain angle. Now minus Q is here, plus Q is here. Forces are acting in these directions. Okay. Now in between the line of action of this force and line of action of the other force, the shortest distance be equal to this. Let me call this dipole as AB and this point as C. Now VC is the shortest distance between the line of action of two forces, and BC is here called arm length. What is it called? Arm length. That is the perpendicular distance between the two forces. That is perpendicular distance between the two forces. Okay. Now, the dipole moment, if you consider, every dipole must be characterized in terms of dipole moment. It is always directed from negative to positive charge. I call that as P. Whereas electric field is always directed from positive to negative. This is electric intensity. Let the angle between intensity and the dipole moment be equal to some theta. Theta is the angle between electric intensity and dipole moment. If this is theta, then essentially this angle is also theta, because the two are alternate to each other. Now if this is theta, to find the arm length, I make use of a trigonometric function. One more thing you must observe here. E length total dipole length alva. Total dipole length can be marked as what? Total dipole length has been marked as 2a. Therefore, from this diagram, I can write cos theta, or I can select sin theta. Sin theta is equal to, if this is theta, sin theta involves opposite side and hypotenuse. Hypotenuse length is known to you. You want the arm length. So sin theta is equal to BC divided by AB. BC is equal to, BC is arm length which is not known, and AB is equal to 2A. Therefore, BC can be written as 2A sin theta. I think you have understood this. I will call this as equation 1. Now my intention is to find out the torque. What is torque given by? We know that torque is given by, first year PUC given by force into arm length, isn't it? Force into arm length in magnitude. So torque is equal to, what is force? Force is EQ. We have calculated here. Force is EQ. In place of force I am writing EQ. What is arm length? Or else I can do one thing. I will call this as 1 and let this be 2. EQ. Arm length is nothing but 2A sin theta. 2A sin theta. Therefore, torque is equal to 2AQ. The product can be written as what? Dipole moment. So, EP sin theta EP sine theta. So this is the magnitude of torque the the dipole is experiencing. Now, EP sine theta into a unit vector in that direction. Or I can rewrite this as, anyway, a vector without arrow, if you write it as its magnitude. So therefore I write E as magnitude of P. P is also a vector, but I didn't put that arrow. Therefore I should consider it as its magnitude. Dipole moment vector magnitude. Sine theta into n cap. Okay. So this is the final expression for torque. Is it not looking like mod A mod B sine theta into n cap? But first year lo odiddri A cross B is equal to mod A mod B sine theta into n cap. Is it not looking like the same? Therefore you can express this as the cross product of two vectors. Torque is equal to, observe carefully, E cross P. We change the field direction. If I reverse the field direction, it can be P cross E, one among the two. How to judge this direction? How to judge this direction? For that, while solving the problem, I'll explain. But you must go through the first year content once to understand these two things. Cross product andre eno, yav direction yav tara baribeku. Idanna first year content once odi. In the next class, while solving the problems, I'll come back to this discussion. You must explain me. Yavudku yavudu anta. In our WhatsApp group, we must put this. Okay? Yavudku yavudu anta. Our direction judge ಮಾಡೋದು ನೀವು ಮಾಡಬೇಕು. ಅದಕ್ಕೆ ನಾವು right hand thumb rule ಅಂತೆಲ್ಲ first year ಲೆಲ್ಲ ಯೂಸ್ ಮಾಡಿದ್ವು in the rotational motion and rigid body dynamics. Such results are useful. You must think about that. Okay. So this is about torque on a dipole. Question will be something like this. Obtain an expression for the torque on a dipole. For that, you must do this derivation. I think you have understood. Once you know whether you have followed all the steps or not. What did we do? Initially, we calculated force and arm length. Later, we got the definition of torque as product of force and arm length. We substituted the values and we ended up with the result. Okay? Is equal to EP sine theta in magnitude. See, if you consider a dipole placed in an electric field like this, electric field direction from positive to negative, positive charge and negative charge, the two charges of the dipole like this. Dipole moment direction is from negative charge to dipole, negative charge of the dipole to positive charge. Electric field like this, the angle in between is 90. When the angle is 90, the two forces have been separated by a very long distance. Arm length is very large. Now if you consider the other case, in a turned position, try to follow. This is the arm length. Now arm length got reduced, isn't it? Line of action of this force, they have been separated now by a distance something smaller than the actual length of dipole. Now torque is force into arm length. When arm length reduces, torque reduces. When arm length is maximum, torque is maximum. Therefore, when this angle is 90 degree, torque is maximum. For theta equal to 90 degree, torque is torque maximum. And maximum torque is just given by EP, because sin theta becomes sin 90. Sin 90 is 1. This is the maximum torque. But if you consider a situation something different from that. Try to follow. This is positive, this is negative. Now I have placed a dipole like this. Negative charge is direct facing the positive plate. Positive charge of the dipole is facing the negative plate. See, in this case what happens? Carefully observe. Electric field is directed from positive to negative. Electric field. Dipole moment is directed from negative charge of the dipole to positive charge of the dipole. So both the things are in the same direction. ಈ ಕೇಸಲ್ಲಿ ನಾವು ನೆಗೆಟಿವ್ ನ ಪಾಸಿಟಿವ್ ಎಳಿತಾ ಇದೆ, ಪಾಸಿಟಿವ್ ನ ನೆಗೆಟಿವ್ ಎಳಿತಾ ಇದೆ. When a dipole is being pulled like this in both the directions, it will not experience turning effect. Torque on that will be zero, no rotation. In this case, torque is equal to EP sin 0. Torque is equal to 0. Torque is equal to 0. Torque on a dipole will be 0 if the angle between dipole moment and electric field is 0. So let me consider the other case. Even then, positive repels positive, negative repels negative. Now the dipole is experiencing two forces which are tending to compress the dipole, which will not set the dipole into rotational motion. So in this case, dipole moment direction is negative to positive. Electric field direction is from positive to negative, isn't it? The angle in between the two is 180 degree. For theta equal to 180 degree, torque is equal to EP sin 180. Torque is equal to 0. Okay, this is the torque. So 0 torque will be experienced. Torque is equal to 0 if theta is 0 or 180 degree. Must remember. This is called stable equilibrium and this is called unstable equilibrium. Why it is unstable? See, ಈಗ pushing action ಅಲ್ಲಿ ಸ್ವಲ್ಪ ವ್ಯತ್ಯಾಸ ಆಗಿ ಒಂಚೂರು tilt ಆದ್ರೂ suddenly dipole turns. Stability is not there. Whereas in case of pulling action, ಒಂದು ಈ ಕಡೆ ಆದರೆ, even if some disturbance is caused, it can realign the dipole into that direction. ಹಾಗಾಗಿ it is stable equilibrium, that is not a stable equilibrium, and this is the maximum torque. Okay, I think you have followed the different cases of torque. Okay, but remember one point: when you consider a dipole placed in a uniform electric field, when you consider a dipole placed in a uniform electric field, you must note this important point. In a uniform in an uniform in ಬೇಕಾಗಿಲ್ಲ, since this is being pronounced with the u, ಇದನ್ನ o ಅಂತ ಪ್ರೊನೌನ್ಸ್ ಮಾಡ್ತಾ ಇಲ್ಲ, u ಅಂತ ಮಾಡುವಾಗ you can write here a only. In a uniform electric field, you must remember torque is non-zero for different angles, but net force on the dipole is always equal to 0, because there are two. I think you have understood all the concepts. We have by now finished the dipole concept. In the next part, we have to follow electric field lines and Gauss theorem. That is the last part of this lesson. We may have to consume 1 or 2 classes for that. In the day or two, we will be able to finish off that. Very important derivations are there. Ella follow madana, carefully observe and try to understand. Okay, we will stop at this point. In the next class, we will continue with the remaining ones.